So let's take a look at our first colligative property. So we want to take a look at vapor pressure lowering. So the pressure above a liquid is called its vapor pressure. Okay, and the figure that we're going to take a look at now, here's this figure. So this shows the vapor pressure of two solutions. One where you're dealing with a pure substance, which is actually the one on the right. Okay, so I'm going to mark this pure. And then on the left-hand side, we're actually taking a look at a solution with a non-volatile substance. So non-volatile substance. Okay, so we want to describe what we're seeing. So I'm going to do that actually on the right over here by the image. So if we take a look at that image on the left, if we take a look at that equilibrium vapor pressure, it's pretty small, but if we take a look at the pure substance, the equilibrium vapor pressure is actually greater. So what are we supposed to get out of this? All right, so here's the conclusion. Non-volatile the solute. So non-volatile solute reduces the distribution of the liquid-gas equilibrium. Okay, and so what that means, if it's reducing the distribution of the liquid-gas equilibrium, then that means that you're going to have less molecules in the gas phase. Okay, and this is actually, the reason for this is actually a consequence of entropy. Okay. So the non-volatile solute in the solution reduces the distribution of the liquid-gas equilibrium, which means less molecules are in the gas phase. If you have a pure solvent, however, and there's no solute there, it's just all solvent, you're going to have a lot more molecules in the gas phase, which means you're going to have a greater vapor pressure. So there is actually a mathematical relationship that we're dealing with here that we call Raoult's law. And there's actually an equation that describes what we're looking at. So if we know the pressure of the solution, okay, this is going to be equal to the pressure of the pure solution times the mole fraction of the solution. All right, so that's Raoult's law. Okay, so again, I'm going to make a note here that the superscript 0, the not symbol, again, this is going to be the pure solvent. Okay. All right, so this is pretty straightforward. If 10% of the molecules are non-volatile solutes, then the vapor pressure of the solution is going to be 10% less than that of the pure solvent. So depending on what the mole fraction is, you'll just take the mole fraction, multiply it by the vapor pressure of your pure solution, and then there you go. There's your vapor pressure. All right, so let's try an example out. How many grams of sucrose must be added to 320 grams of water to lower the vapor pressure by 1.5 millimeters of mercury at 25 degrees Celsius? The vapor pressure of water at 25 degrees Celsius is 23.8 millimeters of mercury, and the molar mass, molar mass of sucrose is 342.3 grams per mole. All right, so let's think this out. Okay, so we want to talk about the pressure of the solution. The vapor pressure of the solution is going to be equal to the pressure of the solvent, the vapor pressure of pure solvent, minus the vapor pressure depression. Now, we're told that the vapor pressure of pure water is 23.8 millimeters of mercury. So let's put that in, 23.8 millimeters mercury. Now, we know that the vapor pressure was depressed by this much, by 1.5 millimeters of mercury. So let's pop that in. All right, so 1.5 millimeters of mercury. Okay, so 23.8 minus 1.5, that should give us 22.3 millimeters of mercury. So that's going to be the pressure of the solution. All right. Now, in order to help us get to this, we need to know we need to actually figure out the mole fraction. So if we wanted to figure out the mole fraction of the solvent, this would be equal to the pressure, the vapor pressure of the solution, divided by the pressure, the vapor pressure of the solvent. Now, we know what the vapor pressure of the solvent is. Okay. So that's 23.8 millimeters of mercury. And we just did the vapor pressure of the solution, which is 22.3. So if we pop that in, so if we say that the vapor pressure of the solution of let me get there. Okay, so if we know that the vapor pressure of the solution was 22.3 millimeters of mercury divided by the vapor pressure of the solvent, which was 23.8 millimeters of mercury, which is what we were told at the beginning of the problem, those two divided by each other should give us a mole fraction of 0.937. All right, so we can this, and again, we define mole fraction. This is going to be the moles of the solvent divided by total moles. So that's what we just figured out. Now, we're told that the solvent, the mass of the solvent is 320 grams. All right. So we know we have 320 grams of water. And if we convert this from grams to moles, okay, so 1 mole of water is going to be 18 grams. Okay, that should give us 17.8 moles of water, which we would pop in over here into the mole fraction. So we can actually figure out the total number of moles of everything. So if we multiply, if we pop that in, so we have 0.937, this is equal to the moles of water, 17.8 moles, divided by the total. Okay, so if we multiply both sides by the total number of moles, we can actually rearrange this so that way we solve for the total moles, which would be the 17.8 moles of water divided by the mole fraction, 0.937. So that way the total moles is going to be 18.9, oops, that's not a 9, 18.99 moles. So remember that 18.99, that's the number of moles of water plus the sucrose. So we know the number of moles of water. So if we take 18.99 moles and subtract 17.8 moles, we should get that there's 1.19 moles of sucrose. Okay, so we're getting there. So now what the problem originally wanted us to find was the grams of sucrose. So now that we know moles, now we just have to convert from moles to grams. So 1.19 moles of sucrose, okay, We know the problem actually told us what the molar mass of sucrose was, which was 342.3 grams. So 342.3 grams of sucrose divided by over 1 mole of sucrose. So that way the moles cancel out with each other. 1.19 times 342. That should give us 407.34 grams of sucrose. And if we follow sig fig laws, that should give us about 407 grams of sucrose. And so that's how you would attempt this problem. So what we just did works if you're dealing with a solute that's a covalent compound that's not going to break down or dissociate in solution. Okay, so that it's very straightforward if you're dealing with covalent compounds, if those are your solutes. What if you're dealing with a solute that does dissociate in water? So things get a little bit more dicey here for ionic solids in solution that do dissociate. Okay, so if we take a look at let's talk about a normal ionic solid. So what if you take a look at potassium nitrate in water? So KNO3 is in water. It's a solid. We put this in water, and it breaks down. It dissociates to give us K plus and NO3 minus. Okay, so it breaks down and gives us that. Now, each unit of the salt, so 1 molecule of the salt gave us 2 non-volatile solute particles. Now, they're actually smaller than the original salt, but within the context of Raoult's law, the vapor effect of the vapor pressure is actually doubled. It's actually a little bit less because dissociation is not 100% perfect, but it's going to be pretty close. Now, the name for that multiplier, this doubled effect, this is called the Van 't Hoff factor. And we represent the Van 't Hoff factor as a lowercase I. And this, the way that we define that lowercase I, this is actually a ratio. This is going to be the moles of particles in solution divided by the moles of solute dissolved. So if we try to figure out the ratio, the Van 't Hoff factor, for our example up here, we know that we've got 2 molecules, so we get a K plus and an NO3 minus. So those are the number of moles of particles in solution. We started, the solute dissolved, we start with 1 mole. So for us, the Van 't Hoff factor would be 2 over 1, or 2. And so that's how we're getting that the vapor pressure actually doubled. All right, so let's now consider the theory behind vapor pressure lowering. What is the equation that we use to calculate Gibbs free energy? And so that's delta G is equal to delta H, the enthalpy, minus T delta S, the entropy. Now, favorability is associated with a negative delta G. So how does the Gibbs free energy of vapor pressure change with the addition of a non-volatile solute? Okay, so if delta G favorability is associated with a negative delta G, we want delta G to be negative. So how does this change with the addition of adding another solute? So let's take a look at this. So the change in enthalpy of vapor pressure, what can we say about this, the sign of this term? It's going to be positive. So given the process of vaporization, the value is not much affected by the presence of a non-volatile solute, so we actually consider it unchanged. Now, entropy, however, is going to be different than a liquid, okay? And so that's what we're looking at in this equation. All right, now because the entropy of the solvent in a solution is higher than the pure solvent to begin with, the entropy for the vapor is going to be smaller than that for the solution than for pure solvent. And as a result, the vaporization of the solvent from the solution is less favored. So it's going to be a smaller negative delta G value, and the vapor pressure is going to be lowered. So, putting this all together, given the minus sign in front of the entropy term, because it's going to be minus T delta S, what does this change in delta S mean for the change in delta G? What about favorability? So it actually becomes, to answer this question, what does the change in delta S mean for the change in delta G? What that means is that it becomes less negative. Okay. Now, what does it mean about the favorability? What that means for us is that the vaporization is less favored. So it would actually prefer to stay in a liquid instead of going to gas. Okay. Now, one more thing that we got to talk about before we jump into Raoult's law, before we do the next problem. Let's define Raoult's law again. So remember, Raoult's law was you got the vapor pressure was equal of the solution was equal to the mole fraction times the vapor pressure pure solvent. So in this case, the change in vapor pressure is going to be equal to the pressure of pure component A times the mole fraction of A. And if we include that Van 't Hoff factor, it's going to be right in the front. All right. So that being said, now that we've got that information out, let's try this problem. What is the vapor pressure in millimeters of mercury of a solution made by dissolving 10 grams of calcium chloride in 100 grams of water at 70 degrees Celsius, assuming a Van 't Hoff factor of 2.7? The vapor pressure of pure water at 70 degrees is 233.7 millimeters of mercury. All right, so first off, let's figure out what we got. So using Raoult's law, we've got the pressure of the solution is equal to the pressure of pure water times the mole fraction of water. Okay. Now, what about that Van 't Hoff factor? We're gonna incorporate that in a bit. Okay. Now we know that this 233.7, this is going to be your vapor pressure right there, pressure of pure water. Now the only thing that we're missing though to figure this out, this is the pressure of the solution is what we're looking for. The only thing that we're missing now is that mole fraction. So we got to get the mole fraction first before we can use this equation. All right, so we're told that we got 10 grams of calcium chloride and 100 grams of water. So we're actually told how much of stuff we've got. So if we do the moles of water first, we know we have 100 grams of water. If we convert this from grams to moles, 1 mole over 18 grams, that should give us 5.55 moles of water. All right, so what about the calcium chloride? Let's try that. Moles of calcium chloride. So you have 10 grams of calcium chloride, and we need to convert that to moles. The molar mass of calcium chloride is 110. Okay, so that way grams cancel out, we're in moles, and we should get a value of 0.09. 0.09 moles. Okay, now here's the deal. Calcium chloride is an ionic compound that will dissociate in water. So if we take this 0.09 moles, what we're going to do now is multiply it by the Van 't Hoff factor 2.7. So now what we're doing is accounting for the extra amount for the dissociation of that compound. So 0.09 times 2.7 will give us about 0.243 moles of calcium chloride that's dissolved and dissociated. Okay. All right, so now that we know that, we can actually figure out the mole fraction. So the mole fraction of water is going to be equal to the moles of water, which we got as 5.55 moles, divided by 5.55 moles of water plus 0.243 moles of calcium chloride. Okay. All right, so if we do this, 5.55 divided by the sum of 5.55 plus 2.243, that should give us a mole fraction of 0.958. And so that's actually the value that we're going to put at the top. All right, so that being said, going back over here to the top of our problem, we know what the mole fraction of water is. We know the vapor pressure of pure water, which was 233.7 millimeters of mercury. We're going to multiply that by the mole fraction. It was 0.958. So 233.7 times 0.958, that should give us 223.88 millimeters of mercury. So that's actually what the vapor pressure of the solution should be. So when we've been talking about Raoult's law so far, we've been talking about a solute that's non-volatile. So now we're going to switch gears and talk about something that is volatile. So what the hell does volatile actually mean? So let's talk about this. So in this case, the way that we're defining volatile is that the boiling point or the melting point, whichever you're looking at, depending on what your solute and solvent is, the boiling point or the melting point of the solute is close to the boiling point or melting point of your solvent. It could be really close to each other, like within 20 degrees. Or it could be the boiling point of your solute could potentially be lower, or it could potentially be higher, which of the solvent, which gets into this whole really bizarre situation. So now so in the first time when we talked about the Van 't Hoff factor and we talked about the last couple examples, I picked compounds that have wildly different boiling points or melting points, so that way we don't have to worry about one of those melting or boiling out. So now we're going to talk about something that does have boiling points pretty close together to each other. All right, so we're going to look at solutions with a volatile solute. So in chapter 5, we talked about Dalton's law of partial pressures, which says this, that the total pressure of a system is going to be equal to the sum of all the pressures. So if you have two components, component A and component B, the total pressure would be the pressure component A plus the pressure component B. If you add those two together, you'll get the total pressure. Now, if I combine this with Raoult's law, we would get this. The total pressure of our system would be the pressure of component A, which we define as the mole fraction of A times the vapor pressure of pure A. Okay, so that's the pressure of A. And we're going to do the same thing for B. The mole fraction of B times the vapor pressure of pure B. And so if we add those two together, that gives us the total pressure. All right, so what we're looking at now is a two-component system. We're using benzene and toluene. Okay, so in the question here that we're asking is, what is the pressure of the system if you have a mixture that's 60% toluene and 40% benzene? So these graphs, we got a lot of stuff going on in this figure. So let's take a look at this. So you've got three different curves. Okay, so one curve, the one that's pink, so we'll start at the bottom, before we take a look at the graphs, we should also look at the axes because this is really important. The y-axis is going to have vapor pressure measured in millimeters of mercury. The x-axis is something that we haven't quite seen before. So this is going to be mole fraction. Now, since we've got two components, one component is going to be measured left to right, and that's going to be the mole fraction of toluene. So you start from the left, you're assuming you've got no toluene, and go all the way to the right, you've got all toluene. Now, the other way, if we measure right to left, we're looking at the mole fraction of benzene. So on the right, we're assuming you've got 100% benzene. On the right, we're assuming 0% benzene. On the left, you're assuming 100% benzene. Okay, so now we can look at these the curves. The pink graph, this is the vapor pressure of pure toluene. Okay. The blue graph is going to be the vapor pressure of pure benzene. And then the green is going to be both of them. The mixture of the two. Okay. So here's where things get a little pretty cool. So if we go all the way, if we assume that we have 100% benzene, okay, so we go all the way to the left, to the end of the blue graph, that is the vapor pressure of pure benzene. Okay, and at this graph assumes that we're keeping temperature constant. Okay, all right. So that being said, if we take a look at the blue line, which again, that's the vapor pressure of pure benzene, that's the pressure of benzene. If we assume we've got 100% benzene, the vapor pressure of pure benzene is going to be 96 millimeters of mercury. If we go down to the pink line, to the vapor pressure of toluene, if we have 100% toluene, that pressure is going to be 30.3 millimeters of mercury. So what we want to know is, what is the pressure of the system if you have a mixture that's 60% toluene and 40% benzene? Okay, so if we go to there, 40% benzene and 60% toluene, that's ideally that point. So easiest way is to go all the way up. And that line is not straight. Let me see if I can do that again. There we go. That's a little bit better. That point right there on the curve, that should be the vapor pressure of both benzene and toluene added together. Okay, but here's where it gets really cool. If I measure, and let me erase this arrow. If I measure going from 0 to where this line hits for toluene, okay, and that's pretty close to almost 20 degrees, or 20 millimeters of mercury. If I go up to the benzene line and measure all the way from benzene to where it connects on that, where we hit that green line, that should be almost the same. That should be about the same for both, or for those. So if this is about 20 millimeters of mercury, that too over here, the difference between the blue and the green lines, that too should also be 20 millimeters of mercury. So they should be the same. So that's pretty cool. All right, so that being said, now that we talked about Raoult's law with the two-component system, we've taken a look at a graph, let's try a problem out. All right, so here it is. What is the vapor pressure of the solution if 25 grams of water is dissolved in 100 grams of ethyl alcohol at 25 degrees Celsius? The vapor pressure of pure water is 23.8 millimeters of mercury, and the vapor pressure of ethyl alcohol is 6.2 millimeters of mercury at 25 degrees Celsius. All right, so we want to know the vapor pressure of the solution. So going back here to our equation, we want to know this. That's what we're solving. Now, we know the vapor pressure of pure A and the vapor pressure of pure B. pure A is water, pure B is ethyl alcohol. We need to know the mole fractions. So to use this equation, we need to know our mole fractions. Now we're told that we've got 25 grams of water and 100 grams of ethyl alcohol. So we just have to figure out the number of moles of both of those, add them together, get the mole fractions. So let's do that. So let's figure out the moles of water first. So you've got 25 grams of water. Okay. And if we convert this from grams to moles, you have 18 grams for every 1 mole. So that should give us 1.39 moles of water. Okay. If we do the same thing for moles of ethyl alcohol, you're told you have 100 grams of ethyl alcohol, which I'm going to shorthand as ETOH. If we convert this from grams to moles, 1 mole of ethyl alcohol should have a molar mass of 46.07 grams. Okay, so if we convert from grams to moles, that should give us 2.17 moles of ethyl alcohol, ETOH. So that being said, we can find, now that we have the moles of both, we could find the mole fraction of water. So the mole fraction would be 1.39 moles of water divided by the total, which is going to be 1.39 moles of water plus 2.17 moles of ethyl alcohol. So if you take 1.39 divided by 1.39 plus 2.17, that should give us 0.390. And so now we know the mole fraction of our water. If we want to know the mole fraction of ethyl alcohol, if we take 1 minus the mole fraction of water, that should give us 0.610. All right, so now we know our mole fractions. If we take our equation, which the total pressure of the system is going to be equal to the pressure of pure component A, in this case I'm going to replace A with water, times the mole fraction of water, plus the pressure of pure ethyl alcohol, times the mole fraction of ethyl alcohol. We can just pop in our numbers. So the pressure of pure water was 23.8 millimeters of mercury. Okay, times the mole fraction of water, which was 0.390, plus the pressure of pure ethanol, that was 6.2 millimeters of mercury, times the mole fraction of ethanol, which is 0.610. So if we multiply those two numbers together and add them up, the total pressure should be equal to 13.06 millimeters of mercury. And so that's how Raoult's law works for a two-component system.